Welcome. This is now video number 5 on the construction of hyperreal numbers. Let me first define the vocabulary we will be using. A hyperreal X is said to be limited if it exists two real numbers a and b such that X is between a and b. For example, -2 or pi plus 2 epsilon, epsilon being any infinitesimal. We say that a number is positive or negative unlimited if for all real number a we have a smaller than x or x smaller than a. Simple examples are given here. We say that a number is unlimited if it is either positive or negative unlimited. We say a number is a positive infinitesimal if it is larger than 0 but smaller than any positive real number. We also define a negative infinitesimal in a similar way. And we say that a number is infinitesimal if it's either positive or negative infinitesimal or 0. We also say that a number is appreciable if it is neither an infinitesimal nor unlimited number. And finally, we will be careful to use the terms limited and unlimited numbers and to avoid the terms finite number and infinite number, which can lead to confusion. Here is how we are going to write the set of limited and infinitesimal numbers. We note that I is a subset of L. If we want, we could also write the set of unlimited numbers as a set of hyperreal numbers from which we remove all limited numbers. And we can write the set of appreciable numbers as a set of limited numbers from which we remove the set of infinitesimals. And here I made a mistake. There is no need for the stars that are here. Let us define epsilon and delta two infinitesimal, b and c two appreciable numbers, and h and k two unlimited numbers. Then all the following operations give an infinitesimal number. For example, the sum of two infinitesimal or an infinitesimal times an appreciable number. Here is a list of all operations giving an unlimited number. For example, the sum of an unlimited number with an infinitesimal, or the product of two unlimited numbers. And here is a list of operations giving an appreciable number. There are a few cases which require further investigation. In the same way, when we have two functions f and g converging to 0, determining the limit of the ratio f over g is only possible if you have some more information telling you how fast f and g are converging. In the same way, when you have two diverging functions, you will need more information if you hope to find out what the difference f minus g tends to. For hyperreal numbers, we have indeterminate forms which are the following. Let us take an example with n and m being the equivalent classes of the sequence you see here. Then we see that the ratio n over m is the equivalence class of a sequence converging to 0. So it is an infinitesimal, which tells us that m over n is an unlimited number. Here, I define h and k two unlimited numbers, for which we see that the ratio k over h is the equivalence class of a constant sequence 2, and it's a limited number. And you can also verify that k minus h is equal to h, which is of course telling us that k is 2 star 2h. Notation that we may often simplify to simply k equal to h. Here comes the fun part, also sometimes confusing or frustrating part. So let me write again what is h and n, those two numbers, and we calculate n minus h, which we can see agrees with h on an infinite set. In addition, n minus h agree with h minus 1 on the complement, which is also infinite. Since only one of those two sets belong to the ultrafilter, all we can say is that n minus h is either h minus 1 or h, but in both cases, it's an unlimited number. In fact, we can build plenty of examples like this one. Take a and b two real numbers and build the sequence t, which is a succession of a,b's. One of the set where the elements of t are equal to a, or the elements of t are equal to b, belongs to the ultrafilter, which tells us that the equivalence class of t is either star a or star b. If you then define the sequence t tilde as a succession of ba, then you can say that if the equivalence class of t is star a, then the equivalence class of t tilde is star b, or the opposite, if the equivalence class of t is star b, then the equivalence class of t tilde is star a. So in the previous example, the equivalence class of t and t tilde were limited numbers, but this doesn't have to be this way. Let's, for example, here define a as a real number, and we construct the sequence t as a succession 1, 3, 5, 7 with a between each element. Then we see that t agrees with n on an infinite set, but we can also construct t tilde as a succession 2, 4, 6 with a between each element. And we see that t tilde agrees with n on the set which is a complement here. So this is telling us that either the equivalent class of t is n and the equivalence class of t tilde is star a, or the equivalence class of t is star a and the equivalence class of t tilde is n. But here we don't have two limited numbers, we have on one side an unlimited number, capital N, and on the other side star a, which is a limited number. This raises a few questions. First, are we free to choose what set is in the ultrafilter? If so, does that mean there are many possible ultrafilters? And does choosing one ultrafilter instead of another is going to have consequences on the field of hyperreal that we are trying to construct? These are questions we will try to address in future videos. Let me switch gears here and move on to something else. I write here the set of limited and infinitesimal numbers. Both sets are subring of the hyperreal numbers, which means they are closed under addition and multiplication. Both addition and multiplication are associative binary operations satisfying the distributive property. We have an additive and multiplicative identity. We have an additive inverse for every element, but we do not have a multiplicative inverse for every element. For example, epsilon, which is an infinitely small, belongs to I and L, but 1 over epsilon does not belong to the set I or L. The question we would like to answer now is, what is the quotient L over I? Well, L over I is defined here as a set of equivalence relation modulo I. So I need first to tell you what is this new equivalence relation. We say that A is equivalent to B if and only if A minus B is an infinitesimal. So the equivalence class of A modulo I is the set of all limited numbers B such that B minus A is an infinitesimal. You can think of B, of all the elements B, that you can write A plus an infinitesimal. Now that we have a new equivalence relation, we need to verify compatibility between the equivalence relation and addition and multiplication. I'm not going to do it, but once you have managed to do that, you can safely define a binary operation, addition and multiplication in fact, between equivalence classes. You can then verify that the quotient set with the binary operation addition or multiplication is closed, that the binary operation is associative, and that we have an identity for each binary operation. The additive identity is the equivalence class of 0, which is a set of infinitesimal. The multiplicative identity is the equivalence class of 1, which is all the numbers you can write mu plus 1, mu being an infinitesimal. You can also verify that we have an additive inverse and a multiplicative inverse for every element. I have mentioned earlier that epsilon, or in fact any infinitesimal, did not have an inverse that was inside the set of limited number, or inside I in fact. Now we see that epsilon belongs to the equivalence class of 0, which is the only non-invertible element in the quotient set. So we conclude that the quotient set under addition and multiplication forms a field. Let us now define the map M from the set of real numbers to the quotient set. We can easily verify that M is a homomorphism. So now, if we can show that M is bijective, then we have proven that L over I and R are essentially the same object. We can easily prove injectivity, which simply comes from the fact that two real numbers are not infinitely close, or in other words, the difference between two real numbers is always an appreciable number. Proving surjectivity is a little harder. It comes down to being able to show that every limited element of star R is infinitely close to a real number. This is something which is true, but we will cover it in the next video.